Our solar system is usually shown as a flat disk, 8 planets circling the sun on a neat, tidy plane. It makes for clean diagrams, it's easy to visualize, but it raises an obvious question that most people never think to ask. What's above that disk? What's below it? The answer is more interesting than you might expect, because once you leave the familiar plane of the planets, you enter regions that are vast, mysterious, and largely invisible. Structures that surround the solar system in every direction and connects us to the larger galaxy. Before we look above and below, it helps to understand why the planets orbit in a disk at all. Ecliptic. But not everything is perfectly aligned. Mercury is tilted about 7 degrees. Pluto, now classified as a dwarf planet, is tilted nearly 17 degrees. Some comets come in at almost perpendicular angles, like needles piercing a vinyl record. But the main planets, they're all within a few degrees of the same flat plane. The plane of the solar system is tilted about 60 degrees relative to the plane of the Milky Way galaxy. Think about what that means. Result of stars with spiral arms and a central bulge. Our solar system sits within that disk, but it's not aligned with it. We're tilted. The galaxy is often pictured as a flat disk sideways. If this helped you, give it a like and subscribe for more content like this. So when we talk about what's above and below the solar system, we're actually talking about directions that point partly ahead and partly behind us as we orbit the galactic center. The Sun travels around the Milky Way at approximately 515,000 miles per hour. But because of that 60-degree tilt, our motion through the galaxy isn't perfectly horizontal. We're cutting through it at an angle. On Earth, we know what up and down mean. Gravity pulls us toward the ground. The sky is above, the floor is below. Simple. But in space, that logic disappears. There's no fixed floor, no universal ceiling. An astronaut floating in orbit might be upside down compared to another astronaut. But neither of them is wrong. It's all relative. So when astronomers talk about what's above or below the solar system, they're using the ecliptic plane as a reference, the flat disk where the planets orbit. It's an arbitrary choice, but it's useful for mapping what surrounds us. Using that framework, we can explore what exists in the directions perpendicular to the planetary orbits. The first major structure we encounter isn't above or below, it's all around. The Oort Cloud is a theoretical shell of icy objects that completely surround the solar system in every direction. Unlike the flat disk of planetary orbits, the Oort Cloud is spherical, a vast bubble of frozen debris. It extends from roughly 2,000 astronomical units to as far as 100,000 astronomical units from the Sun. For reference, Neptune orbits at about 30 astronomical units. The Oort Cloud's outer edge is nearly a quarter of the way to the nearest star, Proxima Centauri. This cloud is made of trillions of small frozen bodies, mostly water ice, ammonia, and methane. They're leftover building blocks from the formation of the solar system. These comets take thousands or millions of years to complete one orbit, and they come from all directions, not just the flat plane of the planets. That spherical distribution is the signature of the Oort Cloud. Closer to home, there's another structure that surrounds us in every direction, including above and below the ecliptic. The Sun constantly releases a stream of charged particles called the solar wind. As these particles travel outward, they push against the particles from interstellar space, creating a kind of protective bubble around the entire solar system. This bubble is called the heliosphere. The heliosphere isn't perfectly round. It's more like a distorted teardrop, compressed on the front side and stretched out behind, because the solar system is moving through the galaxy. Think of a boat moving through water. A wave forms at the bow, and a wake trails behind. The heliosphere works similarly. The solar wind pushes outward in all directions, but the pressure from interstellar gas and dust shapes the bubble as we move. The boundary where the solar wind finally slows down and begins interacting with interstellar material is called the heliopause. Beyond that lies interstellar space, the vast, cold region between stars. Voyager 1 crossed the heliopause in 2012. Voyager 2 followed in 2018. They're now traveling through interstellar space, but still technically within the outer reaches of the Oort Cloud. Even in interstellar space, we are not floating in a complete void. The Sun is currently passing through a region called the local interstellar cloud, a patch of slightly denser gas and dust within the broader interstellar medium. As the Sun moves through the galaxy, it encounters different regions, some denser, some more sparse. It's not flat. It surrounds us in 3 dimensions, providing the raw material that the heliosphere pushes against. Zoom out further and we find something remarkable. The solar system sits inside a vast region of space called the local bubble, a cavity approximately 1,000 light-years across, where the density of matter is unusually low. It's like a cosmic void, not empty, but far less dense than the surrounding regions of the galaxy. How did this bubble form? Supernovae. Astronomers estimate that at least 15 supernovae exploded in this region over the past 14 million years. These massive stellar explosions pushed gas and dust outward, carving out the cavity we now occupy. The solar system wasn't always inside this bubble. About 5 million years ago, our path through the galaxy carried us into the local bubble. We entered through its outer wall, a denser region of gas and dust piled up at the edge. We have physical evidence of this journey. Deep-sea sediments on Earth contain elevated levels of iron-60, a radioactive isotope that can only form in supernovae. The timing of these deposits matches when we would have crossed through the bubble shell. The local bubble has walls, denser regions at its edges where material has accumulated. Inside, we're surrounded by a cosmic cavity, and on those walls, new stars are forming, triggered by the compression from ancient explosions. It's like our solar system is floating inside a giant room, surrounded by cosmic walls shaped by stellar deaths that happened millions of years before humans existed. If we zoom out even further, far above and below not just the solar system, but the entire disk of the Milky Way, we find the galactic halo. The Milky Way isn't just a flat disk of stars. Surrounding that disk is a roughly spherical region containing older stars, globular clusters, and possibly large amounts of dark matter. The halo extends far above and below the main galactic plane. It's where some of the oldest objects in the galaxy reside, stars that formed when the universe was young, before the disk structure fully developed. This reminds us that up and down are only meaningful when we agree on a reference. Relative to the ecliptic, we can talk about what's above the solar system. Relative to the galactic plane, we can talk about what's above the Milky Way itself. At every scale, there's structure, there's motion, there's history. When we look at textbook images of the solar system, we see a neat, flat arrangement of planets. It's useful for teaching orbital mechanics, but it gives the wrong impression. The reality is far more complex and far more interesting. Above and below the plane of the planets, we're surrounded by icy debris from the solar system's formation. We're enclosed by a bubble of solar wind pushing against interstellar gas. We're passing through clouds of material between the stars. We're floating inside a vast cavity carved by ancient supernovae. The solar system isn't isolated. It's connected to the galaxy at every level, moving through it, shaped by it, carrying evidence of cosmic events in the very rocks beneath our feet. And perhaps the most remarkable thing is this. Despite all that complexity, the spherical shells, the cosmic bubbles, the supernova debris, the dark matter halos, life emerged on a small, rocky planet near an ordinary star. We're not just observers of this structure, we're part of it. We mentioned Voyager 1 crossing into interstellar space, but its journey is far from over. The spacecraft is still traveling, still sending data, still pushing deeper into the unknown. So, if you enjoyed this video, make sure to hit that like button, share it with your friends, and don't forget to subscribe for more amazing content.